Swayam Prabha. Digital India. Educated India.
In this lecture, we will be talking about the factors affecting the behavior and performance of reinforced soil. As I just mentioned, reinforced soil technique is one thing that took the whole geotechnical construction by storm, and the fact that you see so many flyovers constructed with reinforced soil technology, and particularly in many other applications of pavements and other cases, it has been possible that one can say that this has been a very important technology for infrastructure. And so there are different factors that could affect the behavior of reinforced soil. One is in terms of the reinforcement, the way the reinforcement distribution is done, the soil type, the soil state and construction. In this reinforcement, you have different types of forms, fibers, grids, anchors, bars and strips. Surface properties are important, dimensions are important, strength properties of the geogrid are important, stiffness are important. We will see some of many of these all the factors, like say for example reinforcement, its location is important, orientation is important, the spacing of the reinforcement is important, particle size, gradation, many of these factors are quite important, and we will see how they are important in the case of reinforced soil. As I just mentioned, the forms of it can be many things like steel strips, geogrids, geotextiles, and why is it important is that see some geotextiles, as I said, friction is an important component of reinforced soil. Geotextile is essentially only a frictional behavior, like because it is a smooth, it is a continuous surface, and there is a friction between the soil and the reinforcement that is required for mobilization of tensile force. Whereas say for example, if you are putting anchors, like you have a reinforcement and then you have an anchor at the end, the anchor will give you the pull out resistance. See, as I said, there are two components, one is called frictional resistance and bond resistance. If you put a reinforcement and then one bond like some sort of anchor, it will have a combination of both friction as well as anchor. So like that people have done different types of or the forms of reinforcement, and say for example geogrids are another type, and they have both friction as well as bonding effects. Then the surface properties are very important. Smooth surface will have less friction, whereas roughened surface will have better friction. Dimensions of the reinforcement are very important because the length, thickness, diameter should be obtained. You have to have, say for example, you have to see what is required for you, and so that you can get from manufacturing agency and then put it. They come in some standard lengths. Stiffness is also very important. Okay. So forms of reinforcement, as I said, it can be a strip, it can be a sheet, it can be a grid, like I will just show you. Then it can be an anchor, like you have a reinforcement, you can put an anchor inside. It can be just a simple bar, like a reinforcement bar. It can be, like as I just mentioned, it can be a geogrid. This is most of the time we use it for reinforced slope applications or retaining wall applications. This was use it for bearing capacity and pavement applications. Like see, the thing as I just mentioned, here this is a geogrid, and this is a direction of axial force, and there is a contribution of grid. There are two things here. The interaction takes place between the soil to soil, like here say shear between the soil and plane surface, like here you have. Then you have bearing also like this, like you can see that when you pull a reinforcement like this, the resistance is along this line, and also like this number of bearing elements are there. Okay. So there are, say for example in this case, in this meter length there are 1, 2, 3, 4 materials that are providing bearing. So this is something like this, like say you have a spacing here, you have a B here, and so if you apply a force, there is some sort of bearing resistance that is mobilized, and to satisfy this roughness to be fully rough, it's there is a simple relationship that is given in terms of this simple equation. So, the shape and the form of the reinforcement is quite important. Then dimensions, actually the way that we design is that we just first get some required strength and stiffness from design, and say we try to check if it is available. Say for example, tensile strength is say 30 kilonewton per meter, and we should know what length it is available, because I need, if 7 meters is the height of the retaining, say for example 10 meters is the height of the retaining wall, 0.7 times is the length of the reinforcement required. So, 0.7 times the height will be the length of the reinforcement at every point, and then you also know the spacing. So, I will know the total quantity of the reinforcement required, because you must be able to optimize on the dimensions actually. Essentially, if you get lot of material, you should be able to say for example, you should be able to optimize them. And another important thing is you can even see, the other day I was mentioning, you have a geocomposite also. Geocomposite means it has a tensile properties as well as drainage properties also. So, depending on the application we must be able to, so but then it may come in different shapes. So, many of these things they come in rolls, and you need to have how many number of rolls are required. So, for example, if you ask a company, he will ask you, sir, how many rolls you need. He will not ask you say for example, what is your design and all that. He would be only interested in something some numbers of rolls required, and also he will give you what application, what are the, say for example, if I say I have a reinforced soil application for a retaining wall, he will give you all that retaining wall specifications using their product, and also how to install the product in the field using for their product, and what is the care you should take, all that he will give. So, essentially this is a function of dimensions. So, the design is one should be careful, and also one should be able to optimize, because you should not waste too much of materials also. I will show you later an example in other class, in the subsequent classes, of how it can be optimized. Then stiffness is a very important parameter, like we have two types of thing, geogrid is somewhat stiff, geotextile is flexible, whereas a steel reinforcement is very stiff. So, the stiffness is required for strain mobilization reinforced soil structure. The stress strain characteristics of the reinforcement are linear, we know that, whereas the soil are of non-linear in nature. For a stable condition, the strain developed in the reinforced soil as a result of interaction between the soil and reinforcement needs to be less than those mobilized in the soil alone. So, for example, why you are putting the reinforcement in the soil is essentially to reduce the strains, because lot of strains are taken care of by the reinforcement and not the soil. So, that way what you are expecting is that there is no slip between the soil and reinforcement. Say for example, if you apply some load, now strains are mobilized both in soil and reinforcement. Okay. So, they must work together, like they move together, like soil should have some strain, and the reinforcement also will have the same strain, because it is what is called strain compatibility. Okay. So, we say that there is no slip that occurs. So, this is a very important concept, and so we calculate the corresponding stiffnesses. Soil can be very less in stiffness, but reinforcement is very good in stiffness. Both of them together will give you the composite stiffness. So, that how much of stiffness is there from reinforcement, in fact is a very important point, like E value, right. This is what I just mentioned. It can be a very flexible one, like a geotextile, it can be a very stiff one, it can be like a this is a geogrid, it could be a steel reinforcement also, like steel is very stiff, and that helps, like as I said, the other one I was talking about the state of the soil also. I was telling about the strain compatibility earlier, where the this is a loose soil, this is a loose soil, this is a dense soil, and actually this is available force in the reinforcement, because the available force in the reinforcement, the stress strain curve is very steep in the case of a stiffer material, it is like this, and it is all of them like this, but in the case of loose soil or a dense soil there is a difference. So, when they strain together, then the possibility is that, as I just mentioned the other case, like you take this case, In the case of dense material, the strain required is quite less, whereas in the case of loose material the strain required is quite little more, right. So, this is what I was just mentioning, that this is an important concept. Say even you can take the other way, that say so this is an important concept in terms of understanding what is the strain required and all that. This we will see some more information on this. Why this is very important, because it is very useful to determine the magnitude of tensile strain that develops in the soil and the reinforcement to understand the equilibrium condition. This is useful to ensure that the design values for the reinforcement and the soil resistance can be realistically mobilized together, and the equilibrium can be achieved with the acceptable level of deformation of the structure. What you are looking for is that, say for example, in the case of the compaction is very good, say like then definitely you have a behavior like this, dense material behavior like this, and you can expect that you have the available force in the reinforcement. You have a, say for example, a stiffer reinforcement, it is like this. So, you have a denser material, so you have a force which is quite good, stress in the reinforcement, right. Stress in the reinforcement is like this. So, in the same thing, this is one thing, okay, fine. So, reinforcement distribution is another important factor. We have seen that, say for example, if there is a load applied on the footing and failure planes develop like this. So, you put reinforcement in the horizontal direction. So, the possibility is that the reinforcement will intersect the shear planes, and then it increases the bearing capacity. So, the location, it all depends on the type of failure. Say for example, in the bearing capacity you can just put below the foundation level, but whereas in the case of reinforced slopes, for example, if the failure is occurring like this, you put like this, right. So, once you put, say for example, nailing, you can put like this, and then it prevents the failure occurring. So, location, spacing, orientation of the effect of behavior, they are quite important, and what we have to see is that the reinforcement should be placed in the direction of tensile strains. Like as I just mentioned, you apply some load and a block moves, there is a tensile strain mobilization in this direction, the compressive strains are mobilized in this direction, and that is the way one should see that. And then optimum spacing should be chosen for maximum shear strength, like one should be really judicious in this. And as I just mentioned, I was talking about the orientation the other day, that like I just gave you this simple expression, which is nothing but the strength in reinforced soil because of the orientation, like sin theta plus cos theta into tan phi, okay. This is what I just discussed, and it is a, like you can see that if the orientation is at an angle say 30 to 60 degrees with respect to its failure plane, this is a failure plane, right, in a direct shear box, say for example, this is a direction. So, this is 30 to 60 degrees, if it is there, you are getting a very good effect. What it means is that if you want to get a maximum effect out of the reinforcement, you should be able to incline the say for example the reinforcement in the in that angles. So, you take the case of a bearing capacity application, the failure surfaces develop like this, and if you put a reinforcement, the angle at which the this particular angle is about 30 to 40 degrees in the case of bearing capacity. Even in slopes also roughly it is same, and the fact is that you can see that between 30 to 60 degrees little flat it is it not? So, it is a very important advantage that so for many of the soil engineering applications, if you put a reinforcement, this is a very useful thing to apply for increase in bearing capacity, slope stability and all that, because it is naturally the way that we put geotextiles or geogrids is giving these angles, okay. You do not need to really do something else to really get these angles. See, because the moment you apply load, the failure surface are developing like this, you are just putting a geogrid, and if you really understand what could be the probable failure surface and what could be the angle, it will be in this range, and definitely you can be very sure that it is going to be effective. The other one that I would like to highlight to you is that if the reinforcement is in the direction of tensile strains, okay, like this is a very important concept here, like if the reinforcement is placed in this the same direction, you will have a very good effect, but then other point is that there what is called bonding. See, there are two things that we need. One is that reinforcement should be very force should be developed well in the reinforced soil. That is only possible when it is in the direction of tensile strengths, and the other one is the bonding. See, this is actually pull out resistance. This is like you have a reinforcement here and there is a maximum stress acting on this thing, and if you pull out like this, what happens is that if a maximum stress is more, then you can't pull out, right. So, from bond considerations, I want to give a simple example. If the angle at which the bond is going to be maximum is 90 degrees actually. So, if you apply a vertical load, the bond resistance is very high, okay. But that is actually the preferred direction. See, this is a reinforcement direction. If you want to get the maximum benefit out from the bond, the vertical load should be applied like this, the sigma maximum stress should be applied like this. So, it is 90 degrees, right. So, that is one thing. The other thing is, if tensile force is in this direction, or the tensile reinforcement is going to be very effective. So, here the angle is 0 in terms of the tensile strengths, and in terms of the bond it is 90 degrees. Like if you want to get a very good bond, you should have this angle as 90 degrees actually, okay. Though I am showing you some angle here, the angle ideally is 90 degrees. Here if it is want to be in the direction of tensile strengths, it is just 0, but both are not possible. You have a in between angle, say for example 45, 30 to 40 degrees like you have here. So, which means that there will be a small correction, lesser it is not either in the direction of this to get the maximum benefit out of the tensile action, or it is not in this direction to get the maximum benefit out of the this bond action. So, still it is in a via media which is somewhat reasonably satisfactory. So, what you should do is that the increase in shear strength will be slightly less. The only consequence is that it will be, you may say that you will get a maximum effect like this, but this because of this small minor things, there will be a minor reduction, that is it. So, that is what we should understand. So, these are all in terms of the orientation effects, okay, in terms of the reinforcement. So, spacing of the reinforcement is a function of the forces that need to be resisted, compaction thickness, etc. What it means is that you have a earthquake force or you have some horizontal force that is coming up. Now, you have the friction between the soil and reinforcement should act in the opposite direction. So, higher is the force, higher is the space, lower is the spacing required. Say for example, you take the reinforced earth retaining wall, maximum pressures are at the bottom, like we say Ka gamma h square by 2, right. So, Ka gamma h square by 2 is the maximum pressure. So, that resistance should be given by this geogrids or reinforcement only, and if the spacing is closer, they give a higher the higher force, right, for the same 1 meter length. You calculate at the bottom 1 meter what is actual active force, you balance out by this, that is what we are trying to do. So, spacing is an important factor, and then compaction thickness is another important factor. So, for example, as I just mentioned, many of these geotechnical constructions we do have to do soil compaction, and we have to do for maximum density and all that. So, when you do that, it has some thickness, it can't be like 50 centimeters, it can only be 25 centimeters. So, you have to place in terms of, say for example, if I get a spacing of 50 centimeters from force considerations, I have to use 2 lifts, like 25 centimeters one lift, 25 centimeters one more lift, put a geogrid or a geotextile. Then in some other case, say for example, I get only say in terms of compaction lift thickness only I should discuss, because that is the way that I can place the reinforcement. Otherwise, I can't put a geogrid for, say for example 10 centimeters I cannot put, it is not we should be, it is uneconomical. So, what you should do is that you should just get a geogrid which satisfies that requirement also. So, you have to come out with some number of combinations, because the companies will have different geogrids varieties, grades, like it can be 80 kilonewton, it can be 100 kilonewton, it can be 120 kilonewton. So, if 120 kilonewtons is suitable and it gives somewhat reasonable compactive thickness, it is fine for you. So, there is a combination that we will see in the examples. So, then see the backfill properties are very important, and see normally in codes we specify well graded non corrosive material, and we need to have the following properties like density, gradation, uniform coefficient, pH value, chloride ion content, and all that properties are required, and coefficient of friction between the soil and reinforcement are required. In fact, we say that the friction angle should be not less than 25 degrees or something, okay. And like you can see IRC specifications, we have Indian Roads Congress specifications, we have BS 8006 UK specifications, we have NCMA specifications which are followed internationally. Internationally there are two types of specifications that are normally followed, one is called NCMA specifications and then the BS specifications, and in India we follow IRC specifications. So, they give specifications for cohesionless soils and both cohesive soils also, like they give a specification like this, okay. Like say for example, what it means is that the sizes it can be 100, the size sieve size should be at least 80, sieve size that gradation the material 65 to 100, 45, 15. So, it depends on that. So, the drainage purposes we know that the coefficient of uniformity D60 by D10, right, should be acceptable more than 5. Properties such as all these things are also important, and the effective angle of internal friction of the cohesional layer should be more than 25 degrees. Friction between the fill and the reinforcement elements is an important property to characterize interaction between the soil and reinforcement, and normally we measure from direct shear tests. As I told you that there are a number of tests that one can do. We discussed that how it can be done. We have to subject it to 3 normal stresses and pull out the, you can shear the reinforcement across it. So, you will get, right. And sometimes there is a tendency for if sand is not available, then there is a cohesive soil is also acceptable, but then there are some requirements that it should not have too much liquid limit and plastic index. There are some specifications that are given, and again all of these things are standard. Say for example, you should find out C and friction angle and all those parameters, and make sure that that will not lead to any other difficulty. Say for example, you can't take an expansive soil as a backfill material. You have to choose a backfill material that has a small cohesion and also gives enough frictional properties, okay. This is what I was just mentioning. For example, a simple example that I thought I should show you, that this is a type of reinforcement that they are trying to place here. In this case is a steel strips, okay. It can be even there are many types of materials here, and then this is the way that it is done, and after that it is compacted. You can see how nicely it is there, layers and compacted. So, once the sand is, the material is dumped, it is called backfill material, right. So, this backfill material should be in placed and compact in layers, and heavy equipment should not be coming to 1.5 meters of the wall face. Say for example, this is a wall face, you should not bring in any of the heavy equipment here. It should be only limited to this side, because if you have lot of lateral, because of the compaction, if you induce lot of lateral pressures, the facing will get disturbed, okay. Then there is also some specification that it should be 95% of the standard compaction and all that, and the water content also we have a specification. One should be very careful, one should follow these specifications very strictly. Then the soil state, see there are a number of reasons here. One is, say we said we said cohesive soil is also okay, and then we also said sand is fine, but then soil alone is not sufficient. Soil state, what is the state of the soil and how does it respond? So, for example, at pull out overburden, so for example, in a retaining wall you have 1 meter, 2 meters, 3 meters, there are 3 or 4 depth of overburden is there, or in an excavation depth of overburden is there. So, the state of the soil is very important, Why? Because the overburden is also very important, like say for example as I just mentioned, as you go down the pull out resistance is going to be higher, right, for a reinforcement, and then the active force is also going to be higher. But in the top layers of layer reinforcement the force coming is quite less, but then the pull out resistance is going to be higher. Why? Because I will just, it is easy to pull out a member with a less overburden, right. Like if then the length is short, it can easily come out. So, you need to, because overburden is something, say for example at 1 meter level it is only gamma by into height, it is low, whereas at down it is much higher. So, overburden is an important factor. State of the soil, in fact is it an active state or a K naught state is another important factor, because some soils, say depending, even it depends on the type of reinforcement also, because stiff reinforcement you have seen it needs, they need very minimum strain, very. So, we can say that the soil is in a state of K naught condition, means coefficient of at pressure at rest. So, the state of the soil is at rest, but whereas a geotextile or a geograde they need some sort of deformation, which means that the state of the soil is active condition. So, the state of the soil is very important. Why? Because in design, if you are trying to, actually people have developed design methods also based on this. So, if somebody is using a steel reinforcement, they say if you want to calculate earth pressure you say K naught into gamma h, but if you are using a geotextile reinforcement they say use Ka into gamma h. So, that is the difference it could make in the case of state of the soil. And soil, state of the soil is also that it is like say is it a dense or is it a loose, like we have seen that it should be very dense material. Why? Because it has a tendency for development of negative pore pressures, when this density is quite high, or there is a possibility of what you call the negative pore pressures, it will increase the effective stress. Then drainage conditions. So, we normally calculate effective stress parameters which are based on a proper consideration to drainage, like so degree of saturation is also another important parameter. Say for example, in slopes, if degree of saturation is say it is a dry slope, then the earth pressure is less, but if it is partially saturated, what is happening? Earth pressure is going to be higher, right. Earth pressure is going to be higher, because there is a water pressure partially saturated, and say for example there is a seepage pressure, imagine. So, all these things lead to they affect the performance of the reinforced soil. As I just mentioned, the state of the stress in the reinforced soil needs to be known, to assess also to know the earth pressure distribution behind the retaining wall. So, earth pressure, how do you do that? It is Ka into gamma h. We assume that it is a hydrostatic distribution, in fact, is it not? We assume that the pressure is hydrostatic, like it is like a water force acting. Okay. So, these are all some typical stress strain curves that we see in the case of tests. So, this is in the case of a peak, the dense material stress strain curve is like this, loose it is like this, you have a similar response here. Okay, like essentially this is a pore pressure response, and this is a, in the case of drain test, this is a volume change. Okay. These are typical stress strain responses that one should understand, and one should get these effective stress parameters from triaxial testing only. Why I am asking is, in a directional test we can't measure effective stresses. If there is a provision for measuring effective stresses in a directional box, it is fine, but normally we conventionally use triaxial testing, right. Then there is another thing important I would like to highlight to you is that see the stress strain curve we have seen of the soil is like this, loose sand it is like this. If you have a reinforcement, it will be like this, much steeper. Okay, it will be like this. If you just plot the reinforcement combined soil plus reinforcement, it will be like this, much higher than any of these two, because it takes the load, right. So, why is it is going to be effective? And one more thing is that there is always a question that is it, how is that the peak angle is related to the constant friction angle. I am sure about this. I hope you are aware of these three terms, that say for example, when you do a direct shear test or a triaxial test, you will get friction angle using peak values, like using decidual values, and there is what is called angle of dilatancy. Okay. The angle of dilatancy is an important parameter in reinforced soil, because if you are trying to take peak response, what I just mentioned, that reinforced soil will be like this, it will not dilate, it will not come back, it will not reduce, this type of strain softening will not be there in the case of reinforced soil. So, to calculate the parameters, what you should do is that there is a, so what is that parameter you can take? There is some equation that is given in terms of the phi dash peak is nothing but you have a constant strain angle phi from residual angle and also 0.8 times psi. The psi is that angle of dilatancy which denotes the effect of compactions and the tendency for dilation. Higher angles of dilations denote higher normal stress on the reinforcement, which increases the pull out resistance. Actually what happens is that to pull out when there is a good dilation is not easy, okay, because the compaction induces what is called dilation tendency, the dilation is there, dilation tendency is there. So, but then it can't dilate, and what, because in that process what happens, it holds that reinforcement much higher, much stronger, because effective stress is more now. See, the dilation tendencies will induce more effective stress, right. So, because of that you have some already some effective stress plus the effective stress component due to dilation tendency, which is not dilation is not allowed to take place. So, that pressure, extra pressure is also added. Then there are some important variables that we should see, like so we have seen, we have discussed about the type of reinforcement, the reinforcement and its types, then its distribution. We talked about the properties of the soil, like we should be loose or dense, or it should be clay or sand and all that, and we also discussed about its orientation, and we also discussed about its some more other features. And I must tell you that construction factors play a very significant role in reinforced soil. Why? Because technique, it is a technique, actually the way it constructed is an important thing. If you do not construct a technique, they implement the technique properly in the field, then the possibility is that it may fail. So, technique may be nice, but the way it is done is not good. So, one should understand that the number of factors such as geometry of the structure, compaction, construction system, aesthetics and durability reinforcements, they all affect the earth pressure distribution, tensile forces mobilized in the deformation. Actually, see, you want all these parameters, and finally they are affected by the technique itself. Okay. The amount of compaction should be estimated so that the reinforced members where the compactions are predominant do not fail. Like as I just mentioned, the compaction should not be too close to the wall. If it is too close to the wall, there is a possibility that because of the compaction there is a high lateral pressure, and if it fails, the facing may deform also. It is all that we do not want to have. So, that is one thing one should know. I will give you small examples. How is that? As I said, construction methods are there are so many, right. Like what the way that we do is that it can be constructed with a simple reinforcement like this and put a simple what is called a sheet like this. You come from you put some you have a cover, first you put a cover like this, then put a backfill, then put this bring, say for example you have this is a area, first put the geotextile layer, then put this material here, then again put one more layer of geotextile, put like this. So, you can keep on doing like that. Okay. Here what is that it is special, the soil is actually, the geotextile is somewhat flexible, right. So, the earth pressure will be in the Ka condition, because the it is not stiff, geotextile is not stiff, then it may be more, have a more tendency for deformation. So, it is one thing. Okay. So, it is like this, it may undergo a lot of horizontal movements as well as vertical movements, that is one simple example. Whereas, you take another case where you have a steel reinforcement like this, and it is connected to the facing panels. In such a case, what happens is that as I said, because of the connection between the reinforcement and the panel, some force gets transferred to this. So, which means that one should design the facings properly. Okay. In this case, facing is a simple geotextile material, right. You do not have any simple problem, and then you just put you can put a simple layers of geotextiles, keep on putting it to some height, and then if the tensile forces are taken care of by the geotextile tensile strength, it is all right. Length is also should be, say for example, as I said that if 10 meters is a height, 0.7 times the length of the should be the length of the reinforcement. So, you can just do that, and if you satisfy that condition and then see that the material stands, like you can make a 80° or 90° geotextile slope like this, keep on doing it, take a soil, put the material, take a soil, put that geotextile like that, compact it, of course you have to compact all that. So, you can do that instead of a conventional 1:2 slope, sorry 2:1 slope, where 2 is horizontal and 1 is vertical, like which you do, right. In a embankment problem, we do that, we need a 2:1 slope, which has because a slope factor of safety is cannot give you that steeper slopes, but here with geotextile you can achieve that steeper slope. What is happening here is that the difference is the material the way it is done, geotextile. So, the way it is constructed is an important factor here, like so you have different types of joints also, like this is actually the way that is done. In fact, in the field the way it is done is that it is like you bring that facing panel. See, you construct first half panels like this is one half panel, this is one half panel, this is another one, then you put the next one, they keep on doing, you can observe them in the field. I would like to just illustrate some of these important points with reference to a case study that we did. This is our own underpass at University of Science, and I would like to just illustrate to you how it was done. It was done with a soil nailing. Soil nailing is a classical reinforced soil technique, where you do not need a backfill, in situ soil has to be stabilized, and the way it is done is you make an excavation, just excavate about some say half a meter or something or 1 meter, put some reinforcement like this. This is a road, this is a typical structure, right. So, the advantage is that instead of having a big retaining wall like this, you have a simple reinforcement structure like this, where you have simple systems like this. Okay. So, it is much cost effective, and you do not need to worry about the backfill material for this retaining wall and all that, and it is easy to construct also in an excavation, right. So, this is a very simple advantage, and the way that we have these walls is that in one case you have a 5 meter wall with this type of facing, right, and it has this 3.5 meters is the length of the nails. Okay. Other case we have vertical one. Okay. So, the difference is that you have a stepped facing, which has like 15 centimeters at every place, 15, 15, 15. So, 45 centimeters is the total difference. Why is it done was that if you just incline little bit, the earth pressure will be less. If it is inclined wall, the earth pressure is very high. If it is little inclination is there, the earth pressures are little marginal less, right. So, that we wanted to do that here, and the second case was that it is vertical, where the earth pressures are maximum when the wall is vertical, and we use steel reinforcement, which is nothing but steel rods. So, it is a stiff reinforcement, and we call it we use a k naught gamma h, and so we have a design method based on that, which we call it coherent gravity method. Like once you put a reinforcement like this, what it means is that this wall behaves like a coherent mass. Okay. That is why we say that it is a coherent gravity design method. So, actually you can design this the way that I told you, like how to calculate earth pressure k naught into gamma h, and see that is earth pressure acting, right. So, gamma k naught, so how do you, so what is the pressure that you have to resist, how do you get it? It is nothing but you can, the friction between the soil and reinforcement you have to calculate. How do you get that? T you should get, tensile force in the reinforcement. How do you get? It is nothing but the friction force around the reinforcement 3.5 meters, and SV into SH. What is that frictional force? It is nothing but k naught into gamma h again, right. So, that is earth pressure is coming. So, you have to calculate the frictional force and see that the spacing and vertical and horizontal spacing are in such a manner that the tensile force that is there is transferred back to the system. So, there is a net pressure that is coming here. If you put reinforcement like this, there is a friction develops. So, all that force is again transferred back to the system. So, that is what we do, and if you want to analyze that, conventionally we can design it, like as I said we have some rules where it should be some based on that earth pressure you can calculate SV and SH, and length is also it should be 0.7 times h. That is what you can see what is the length here, 3.5 by 5, 0.7 times. So, but if you want to analyze that properly, we have to do a numerical simulations only, right. For that we have done it here, like the cohesion is about varying cohesion is there, friction angle is 25 degrees, unit weight and all Poisson's ratio is all there, E is 20 MPa, nail properties is a 20 mm diameter, length is 3.5, spacing is 0.5 in one place and 0.4 in another place, modulus of the steel is this much, RCC facing we have, and these are all the properties. So, once you do that, how do you understand the effects of construction here? Let us see that. Actually, so the maximum, see the thing is the way that, see in a numerical simulation the way that we do was that you just excavate a bit and then put reinforcement, right, excavate excavate the soil and then put reinforcement. So, same thing can be modeled also in the numerical analysis, that you excavate and allow it to equilibrium, in the FLAC or finite element analysis. If you just see that what happens, then shear contours will strain contours will develop and all that, and you can calculate what should be the keep on doing the same, put reinforcement and what is the force mobilized in the reinforcement, you can calculate what is the tensile force mobilized in the reinforcement also you can calculate. You can see that, say for example here it is when you excavate up to -1, there is something like minus 2 kilonewtons, then you come to -2 or -3 or -3 meters, like that, there is some change, is it not. So, what is happening is that depending on location, like though the design is based on the same lines, depending on the location, because the small changes in earth pressures are there and C values are also different, C, so you can see that the pattern of tensile forces is different. Okay. It is not like a triangular or something like that, it is not a like we assume some, what this we will see that. So, this is another one. Variation of maximum tensile force in the nails. What we did was that some sort of analysis was done where without nailing it is able to stand for about any with C equal to 10 kPa, it can stand about 2.5 meters without nailing. Okay. So, after that it collapses. So, then what is the depth at which it collapses? It's we got like this, the critical depth of excavation is arrived based on the maximum horizontal deformation exceeding %. Like what is happening, there is horizontal deformation that occurs, and in literature we have seen that about if the deformation is for stable walls, there is some sort of criteria that is given. We followed that criteria and we got these numbers, it can be even 0.1 also, 0.1, 1, whatever, some criteria has been fixed up, and we got these numbers. So, for 10 kPa about 2.5 meters it can stand without nailing. If it is 15 kPa it is 4 meters it can stand, and 20 kPa you do not need nailing at all. But the fact is that it is all cohesion cannot be relied, it is a sandy material, suppose then it can collapse, right. So, what you should do, you should have to supply some sort of what you call cohesion, pseudo cohesion, which is in terms of the soil reinforcement. That is what I just gave you in one of the fundamental principles, that so the advantage of the soil is that it can give apparent cohesion which is permanent, whereas this is I am just doing a parametric study. So, I use this, then another thing is the location of maximum horizontal deformation also we got. Okay. So, these are all depth improvement factors, nothing but 5 by 2.5 is 2, 4 by 7, and these are all the numbers. And we also did some sort of pull out tests that we in one of the for the nail was pulled out, and using some simple equipment that we have, it is a master's program. This is how you can see the nail was done, and this is another arrangement that we have seen, and this is a field pull out test result. And for because we assumed various values of C and phi, because there are some variable values, where this is like a field pull out test, we could match this field. So, what are the values that this field pull out test represent, one can calculate. C and phi are more or less constant, but E one can change and you can get that number. So, what it means is that this particular field pull out test is an important parameter, because when you have so many variables, it is important to calculate what should be the representative C and phi, and it gives that using a pull out test. So, as I just mentioned, now what is the consequence of once you know this properties, how the horizontal deformation will change with respect to different cohesion values. Like you can see that at this it is so high here, and in other case where say for example in the location 1, say this all the 3 points corresponding to location 1, depending on the say C is the highest lowest here. So, you will have higher deformation here. So, like that. Why this thing is, why is it like this, is because of the way it is done. We are exactly simulating the same thing in the field, in the numerical simulations also, like I excavate, then allow the soil to equilibrate and then find out stresses, then put the nail also and calculate what is the deformation and what happened, all that I calculate, and then sequentially if I do, if I plot all these deformations, I will get like this. Okay. So, once you have this sort of information, one can understand, as I said, construction practice, how is that it is influencing here. So, sequence of construction, type of facing, connection between nails and facing, stiffness of the facing, inclination of the facing also, we will just see that. Actually there are two sequences, one we had, one was that 1.5 meters excavated, say actually the total height is 5 meters, right. 1.5 meters can excavate, again 1.5 meters one can excavate, and 1.5 meters one can excavate. Why is it 1.5 meters is required is 2 persons 3 persons can stand and nail it. So, the average height is 1.5 meters. So, 1.5 meters one can comfortably excavate and then start nailing, that is what we thought. And second sequence is the other sequence, I want to say half a meter excavation, put a nail, half a meter again nail, half a meter again nail. So, which is better? Actually the thing is, in the first case where you are putting in 1.5 meters and then putting nailing, already there will be some deformation that get stabilized. So, putting nails later will not be that effective, I mean at least in terms of the deformation. So, like that. So, we did some sort of analysis based on that. You can see that critical depth of see like without nailing it will be lowest, for depending on the C value. The moment I have a sequence 1 which is nothing but 1.5 meters and doing like that, it is much better than that. The best was 0.5 meters and put a nail, 0.5 meters put a nail like that. So, this has a better stability than compared to others. The same thing is also like the other important plot that we should see is that I told you that how do you get the tensile force Ka gamma h into SV into SH or K naught also you can have depending on, if you assume that the soil is yielding, you can put 1 minus sin phi by 1 plus sin phi, or if it is not yielding 1 minus sin phi. Okay. So, this is how it is different than what you assume. This is a type of other one that we have. So, this is what I was telling you, the difference between the sequence 1 and sequence 2. This is another type, effect of inclination. This again the type of vertical facing, it will have maximum deformation compared to other deformations, like we will see that is what we are seeing. This is again same thing, like if you do connection, what happens? When you do with connections, what I just observed was that it will be having higher critical depth of excavation, which means that the forces are little transferred to that, and also the actually we have seen that the failure surface, the shifts towards the facing, and the mass of the soil that creates earth pressure is going to be less. So, this is again about the effect of connections, where the vertical facing without this thing will have the highest pressure, like without facing this has highest pressure. This is another one. So, what I would like to just summarize is that effect of sequence is very important, and these are all some observations that we saw. Rigid connection between nails and facing improve the stability of the soil mass, both in terms of factors of safety or even deformation and all that, and thickness also does not have a significant effect. And so, is it 100 mm is okay or 75 mm is always a question, and some codes recommend some numbers, but then it is important that we have some analysis also done for that. Thank you.